Okay, so let me start with question 5, which is we're gonna calculate and we're gonna see the maximum profit for this question, where they give a table, and from this table we can know that we're going to find maximum profit, and this will be our objective. And besides that, you can take few notes or few points from the below paragraph, which is there are 40 hours of labor and 120 kilogram of clay available each day for production. Formulate this problem as a LP model. So now let me start with LP model. As we know, we can transfer the points or the unit to the LP model, where we will put maximum Z 400x1, which is represented by bowl, and 500x2, which will represent a mark. And then we will go to the both constraints. The first constraint will be x1 plus 2x2, where we can see at here this one will be x1 and this one will be x2, will be lesser than 40 because there are 40 hours of labor and 100 kilogram of clay. So now let's go for the second constraint, which is 4x1 plus 3x2 lesser than 120. And from here we can see that 120 kilograms were given, and over here 4 kilogram and 3 kilogram respectively. Why it is lesser? Because it is a maximum profit. So when the question given maximum, so the constraint sign will be less than, then x1 x2 will be greater than 0.
This is the graph, and I will tell you how to do it. First, you have to know the LP model. Maximum Z equal to 400x1 plus 500x2. Subject to x1 plus 2x2 less than or equal to 40. 4x1 plus 3x2 less than or equal to 120, x1 and x2 more than 0. When you know the LP model, you can make the constraint line. First constraint is x1 plus 2x2 less than or equal to 40. Second constraint is 4x1 plus 3x2 less than or equal to 120. Then make the line like x1 equal to 0, x2 equal to 20. The point is 0, 20. Then let x2 equal to 0, x1 equal to 40. Point is 40, 0. This is the line for first constraint. 0, 20 to 40, 0. This is the constraint. x1 plus 2x2 less than or equal to 40. Don't forget to label it. And then it is less than or equal to, so we have to shade under the graph. For the second constraint, 4x1 plus 3x2 less than or equal to 120, let x1 equal to 0, x2 equal to 40, the point is 0, 40. Let x2 equal to 0 and x1 equal to 30, so the point is 30, 0. So this is the line for the second constraint, from 0, 40 to 30, 0. This is the constraint for x1 plus 3x2 less than or equal to 120. Don't forget to label it. The constraint is less than or equal to, so we have to shade under the graph. After that, we have to find the feasible region. So this is the feasible region, and don't forget to label it to feasible region. After you find the feasible region, you have to make the objective function line. So let z equal to 4000. You can also let z equal to 2000 but it's more accurate to let z equal to 4000. So substitute the 4000 into the function. 4000 equal to 400 x1 plus 500 x2. Let x1 equal to 0, x2 equal to 8. The point is 0, 8. Then let x2 equal to 0, x1 equal to 10. The point is 10, 0. So this is the dotted line for the objective function line from 0, 8 to 10, 0. Use the ruler to find the maximum point. Move it slowly until you find the maximum point. So that is our maximum point. And don't forget to label it. Our optimal solution is x1 equal to 24, x2 equal to 8. Substitute to the function z equal to 400x1 plus 500x2. So the answer is 13,600. That is the final answer.
Okay, for the second method, we can also solve the linear programming model graphically, but this is another method, which is by using an online solver. An online solver is a solver that can easily solve any mathematical problem that we are probably not sure of our answer. So for today, I will be using an online solver called A to Z Math. But specifically for today, I am using the graphical method, so I'm going to just click here. So we have a few suggestions here. So I'm going to click on the first website. Okay, what we got here is the method stating that we are using the graphical method. And it says here that we can solve the linear programming model or linear programming problem using this graphical method calculator. So what we have here is the graphical method calculator. And for our linear programming model today, we have 2 variables and a total of 2 constraints. So just click in generate here. Okay, so what we have been provided here is some space to type in our objective function and our constraints. So for our objective function, it is z equals to 400x1 plus 500x2. And for the first constraint, we should type in 1x1 plus 2x2, and it is less than or equals to, yes, that's correct, 40. Okay, for the second constraint, it is 4x1 plus 3x2 less than or equals to 120. Okay, so it says here that the x1 and x2 should be more than or equals to 0. It means that it should be non-negative. So I forgot to say here that besides the objective function, they're stated here maximum or minimum. So for the LP model today, I would be using maximum. Okay, so just click find and it will do the magic for us. Okay, there will be shown here a few, actually not a few, a lot of information that this website can find from us just typing into the information just now. So it says here that is our LP model and it depicts everything for us. What they give here is a hint. The hint to draw constraints. The hint to draw constraints means that steps on drawing the constraints on the graph. So the first thing to do is to treat our first constraint from inequality sign to equality sign, which is this one. And then we should substitute x1 equals to 0 to find out what x2 will equals to. So when we substitute the 0 into the function here, into our first constraint, then we will get x2 equals to 20. But then what will x1 be when x2 equals to 0? So it states here that x1 will be 40. So we have a small table here just to clarify things. When x1 is 0, x2 is 20, and when x1 is 40, x2 is 0. So for the second constraint, we can find out when x1 is 0, then x2 equals to 40. Then when x2 equals to 0, then x1 is, click here, okay. x1 is 30. So this is another small table that we can gain a little bit of information from the substitution. So from both of these tables, we can now construct lines, which are constraint lines. What is shown here is a graph containing two constraint lines. That is the first constraint line, which is the red one, that is x plus 2y less than or equals to 40. And the second constraint line is the green colored one, which is 4x plus 3y less than or equals to 120. The shaded region here is what we call as feasible region. Feasible region is a region where it satisfies all of the constraints simultaneously. So why does this area satisfy both of these constraints simultaneously? Because based on the first constraint line states here that it is less than or equals to. When it is less than or equals to 40, then we should shade under the constraint line. And for the second constraint line, it also shows here that it is an equality sign of less than or equals to 120. So the area that is shaded is here under the line. So the feasible region is actually the region where both of them overlay each other. Okay, so when we draw the constraint line, two of these constraint lines here, what we get are four edges. So what we call these points are actually extreme points. So these extreme points, we have 4 extreme points here, and we would like to pick one as our optimal solution. If by manually, we would be using the objective function to construct a line and slowly move it forward until we meet the most extreme point. Okay, but using this online solver, it would be obviously much easier. So yes, so they have also given us 4 extreme points labeled O, A, B, and C. Using the extreme point coordinates here, they will automatically substitute all of the values inside the objective function so that we could get the optimal values for 4 of these tested objective functions. So for the first one, for the extreme points that are situated at the origin, which is 0, 0, the optimal value found out is 0. So it is obviously not this one, because we would like to find out the most maximum value. So for the second extreme point coordinates, the optimal value becomes 12,000, and the third 13,600, and the fourth one is 10,000. So what we want to pick is the most maximum value, and the most maximum value is 13,600. So we would like to label B, which is 24H, as the optimal solution, because when we substitute this optimal solution into the objective function, we found out that the optimal value is at the most maximum value. So the conclusion here states that the maximum value of the objective function is z equals to 13,600, and it occurs at the extreme point 24, 8. Hence, the optimal solution to the given LP problem is x1 equals to 24, x2 equals to 8, and the maximum is 13,600.
Let's have a look at this LP problem. To solve this LP problem using Simplex Method, we have to convert this LP problem into standard form. We need to change this equality sign into equal sign for all constraints. The sign for the constraint is less than or equal to, so we need to add slash variable. This is the complete standard form. Then we need to make sure all the right hand side is non-negative. Now that all the right hand side is non-negative, we need to convert this standard form into tableau form. For the initial tableau, insert all the coefficients in the tableau. First, we need to choose the entering variable. Choose the most negative coefficient. We can see that negative 500 is the most negative coefficient. So we can see that x2 is the entering variable. Now we need to choose the leaving variable. We have to choose the smallest ratio. We can see that S1 has the smallest ratio. So S1 is the leaving variable. The intersection for entering variable and the leaving variable is 2. So we need to change this value into 1, and negative 500 is 0, 3 is 0. Now we have to build another tableau and do the ERO. For row 0, the ERO is row 0 plus 500 row 1. For row 1, 1 over 2 row 1. And for the ERO for row 2 is row 2 minus 3 row 1. The intersection between row entering variable and leaving variable is 5 over 2. So we need to change 5 over 2 into 1 and 1 over 2 into 0, negative 150 into 0. Now we need to build another tableau and do ERO for each row. For row 0 plus 150 row 2. For row 1, the ERO is row 1 minus 1 over 2 row 2. ERO for row 2 is 2 over 5 row 2. We can see that there is no non-negative coefficient in row 0. Now, this is the optimal tableau. We can check it one by one. All variables have no negative coefficient in row 0. Yes. All basic variables have 0 coefficient in row 0. Yes. Any and B have 0 coefficient in row 0. No. Thus, LP has a unique optimal solution. So we can write it x1 is 24, x2 is 8, s1 is 0, s2 is 0, z is 13,600. We can check this answer to find if it's correct or not. We can put the value into objective function. So the objective function is z equal to 400x1 plus 500x2. We can insert this value into this objective function. So z is equal to 400 times with 24 and plus with 500 times with 8. We can get the same value with this one.
Okay, this is the primal LP. This is maximum Z equal to 500 x1 plus 400 x2 subject to 2x1 plus x2 less than equal to 40 and 3x1 plus 4x2 less than equal to 120. x1 and x2 greater than 0. Okay, from this we convert it to the dual LP. So for the objective function dual LP, we get it from the right hand side of the primal LP, which is 40y1 plus 120y2. For the constraint dual LP, constraint first, we take it from the first variable of the primal LP. So first variable is 2x1, 3x1. So first constraint of the dual LP is 2y1 plus 3y2. Okay, same as the second constraint, we get it from the second variable of the primal LP, x2 for x2. So we write like this, y1 plus 4y2. Okay, for the right hand side of the dual LP problem, we get it from the objective function of the maximum primal LP, which is 500x1, 400x2. Okay, we take it and rewrite it here, 500 and 400. So y1 and y2 greater than 0. So this is the optimal solution. Okay, from this objective, we change it to the standard form to make it a simpler method. So since the problem is minimum, so we minus E1 to the constraint 1 and minus E2 to the constraint 2. We want to get a sign of equality to make the problem balance. So y1, y2, E1 and E2 greater than 0. Okay, from this standard form, we convert it to the tableau form, initial tableau. So initial tableau for this problem is 2 minus z minus 500x1 minus 400x2 equal to 0. So this is the initial tableau for this problem. So we get it BV, S1 and S2, and BV is S1 and S2. From this tableau, we know it is not optimal, so we have to do the tableau 1. So tableau 1 this. So for the row 1, we do ERO R1 divided by 2. So this is the right hand side of the row 1 is 20. So for row 0, we get ERO row 0 plus 500 row 1. So the right hand side is 0. So for the row 2 minus 3R1 equal to row 2, we get 120. This tableau is not optimal. Because the right hand side of the row 0 is 0. So we have to do it again to do the tableau again. So we find the ratio of the tableau. So the ratio we get 40 and 24. So from this we know the x2 and x1. So x2 and x1. Okay. We get the maximum ratio and the minimum variable. So from that we know we take tableau 2, which is this. So from the tableau we see if optimal, which is right hand side of this table is 30,608 and 24. So from this tableau we can see this is the optimal solution for dual LP. So y1 equal to 160 and y2 is 60. That's all for the simplest method of dual.